Hi everyone, and welcome to part 2 of lesson 8.3, polar form of complex numbers and de Moivre's theorem. In this video, we're focusing just on polar form of complex numbers, changing something from rectangular form into polar form. And that's all we're doing in this lesson. Okay, so rectangular form we're familiar with. A is the real part, B is the imaginary part. But in polar form, we're changing it to have a radius and an angle measure, okay? Now, you may recognize R as something that we were using way back in lesson 8.1 and 8.2, and that's true. We find it the exact same way. So R is the absolute value of RZ, which is A squared plus B squared, and it's the square root of that. Now, you may remember in our past lessons where R was the square root of x squared plus y squared. But remember, A is on the x-axis and B is on the y-axis. So this is basically the same thing. They've just changed to A's and B's rather than x's and y's. And the same thing is true for theta. Remember, to find theta, we had tangent theta equals y over x. Well, in this case, the y values are our b values, and the x values are our a values. So basically, these are the same formulas we used in lesson 8.1. It's just that they've changed it to a's and b's. Okay, so that is how we find these. Now, please notice, cosine is an x value, and sine is a y value, and sine is attached to the I. Okay, so basically these formulas make a lot of sense if you just think through what's going on. Okay, so R, let me just give you a few more words. R is the modulus, and theta is the argument. Okay, R is the modulus and theta is the argument. Okay, polar form is also known as trigonometric form because we're giving it in terms of trig functions. Okay, and one last thing to be careful about, one last thing to note is that you want to watch what quadrant the original function was in, the original polar form was in, because if it was in like second or third quadrant or even fourth quadrant, you want to make sure that these angles are going to get you where you need to be. So I like to just sketch out a quick graph and note which quadrant this would end up in, and then make sure that these angles are from the correct quadrant before I plug them into my polar form equation. So let's take a look at an example. Okay, let's keep that up. Here's our example. So part A, it says they gave us the complex number 1 plus I, and they want us to change this into polar form. So notice A is 1 and B is also, notice the invisible 1 in front of the I, B is 1. So for R, I do 1 squared plus 1 squared and the square root of that. So it's the square root of 2. And for theta, I know tangent of theta is 1 over 1, or just plain old 1. Now, notice that this is going to be in first quadrant because I have a positive x and a positive y. It would graph right about there. So let me get my unit circle to see what value has a tangent of 1 in first quadrant. And I notice that right here at pi over 4, the tangent is going to be 1. So pi over 4 is my argument, my theta value. So I know theta equals pi over 4. Now, all I have to do is put in my R and my theta into my polar form. So this is Z equals square root of 2 times cosine of pi over 4 plus I sine of pi over 4. Okay, let's do another one. I'm going to go down to C so I have room for it. Okay, in part C, notice this graphs We have a negative x and a negative y. It's going to graph in third quadrant, okay? So for r, I have this squared. So I have negative 4 square root 3 squared plus negative 4 squared. When I square this, I'm going to get 16 times 3. And 16 times 3 is 48. And I have to square that. And it's plus 16. Okay? So I need the square root of 48 squared plus 16. Okay? And according to my calculator, that is not a perfect square. It comes out to the square root of 2320. I believe that that can be simplified. Oh, silly me. I already squared. I don't need the square on that. It's a good thing I checked my notes. So 48 plus 16 is 64. And the square root of 64 is 8. Okay, so that is my modulus. Now let's find our argument. So I have tangent of theta equals y over x. So negative 4 over negative 4 square root 3. This reduces to 1 over the square root of 3. And from my unit circle, I'm going to check, and again, I have to make sure I'm in this quadrant, quadrant 3. 1 over the square root of 3, let's see, it's y divided by x. This one would not work, but this one would. It's negative 1/2 divided by this. This would flip, and you would get 1 over the square root of 3. So 7 pi over 6 is the angle I need. Now I just need to put this into my complex number. So I have 8 times cosine of 7 pi over 6 plus I sine of 7 pi over 6. Oops, that's supposed to be a z. Okay. So let's look at another one. Let me just get my eraser. I buried it. There it is. Okay. I promise we'll get to B. I'm going to do D first, so I'm sure I have enough room. So letter D. Okay. We have 3 plus 4i. Notice this is going to be in quadrant 1 because it's 3 over and 4 up. It's up here. And that placement can help you. I should have used that last time. You can tell that it's not as far over but further up. So I should have checked pi over 3 for that one. And I'll see if it works. I don't think it will because 3 and 4 don't seem very unit circle-ish to me. But let's check. Okay, for my argument, modulus. For my modulus, I have 3 squared plus 4 squared, and it's the square root of that, which ends up being 5. Okay, because this is 9 plus 16, which is 25, and the square root of 25 is 5. Now, for theta, I have tangent of theta equals y over x. And this is definitely not on my unit circle. Now, when it's not on your unit circle, you can use your calculator to calculate it for you. Or what I'm going to do for this one is I'm just going to say that theta equals tangent inverse of 4/3. I'm just going to leave it like that. So when I write my final answer, it's going to be a little messy. And all I'm going to do is write 5 times the cosine of the tangent inverse of 4/3 plus I times the sine of tangent inverse of 4/3. Okay, and I did this because I wanted to keep it as accurate as possible. If I get a decimal number from my calculator, it's not going to be very accurate. And with this information, we can make a triangle and then find out what the cosine would be, and then that would help us to get an exact value. Now, one thing I would like to point out is if we did that and we made our triangle, okay, notice, okay, we would have a triangle like this. Oops, didn't need the coordinate plane. With a side tangent is opposite over adjacent, so 3, 4, 5. And the cosine, if I was to put this in, cosine for my theta would be adjacent over hypotenuse, so 3 over 5. And sine for that would be 4 over 5 times I. And all of this is multiplied by 5. So notice, if I go ahead and figure this out, what's going to happen is I'm going to distribute, and I'm going to get the same thing I started with. So, and that works with any complex number in polar form. If you were to work out what the cosine and sine of those angles are, and then you distribute in your R value, you're going to get back to what you started with. Okay, we have one more to do. That's part B that I skipped way before. Okay, part B. I have -1 plus 3i. So for R, I have -1 squared plus the square root of 3 squared. Okay, -1 squared is 1. Square root of 3 squared is 3. So R is the square root of 4, which is 2. And remember, R's are always positive because they are describing an absolute value. Okay, now I know that tangent of theta equals y over x, so square root of 3 over -1. Now I should check what quadrant I'm in so I know which quadrant to look at. X was negative, y was positive. I'm in quadrant 2. Okay, in quadrant 2, notice the square root of 3, which is my y value, is a little more than 1. So I'm going to check this 2 pi over 3 first. So if I do my tangent, I would get square root of 3 divided by -1, which is exactly what I needed. So I'm going to use 2 pi over 3. Okay, and now I just need to put it in. So it's 2 times the cosine of 2 pi over 3 plus I sine 2 pi over 3. And that's it. So that's it for this video. Next video, we'll talk about multiplication, division, and powers. So I'll see you soon.